I've started it, so just take care of it.
So we get those. Yeah.
That's the only thing you can ask. That's really the only way to first section anyway.
I didn't realize.
Okay, good afternoon, everyone. Good afternoon. Thank you for coming. All right, so here is a very brief recap of what we started last class, and I was in the process of completing some of these things. We will go over it very quickly so that we can go on to new things. Okay. We started off with this kind of a first order system, all right, and f of t is defined as a composite type function, which is a combination of several different pieces. Okay, and this is the total function f of t. This is broken into three pieces, and we discussed how this was done in the last class. And I'll present another example, and if that is the only thing we do today, that is also fine. I'll present another example of this type. So this we broke into 2 times r of t times u of t. Okay, so that was this particular function. The second one was -2 because the slope of this ramp is in the negative direction, it's descending. Right, so this is r of t minus 10, u of t minus 10, and I'll talk about this idea of writing everything with the step function included. Third one is minus 20, u of t minus 12.5. Okay, all of these were taken after a certain amount of time had passed, and so that's why you are subtracting it from those time periods. All right. Then we said that the total problem, and this is where we employ the principle of superposition. Principle of superposition is I can take a linear system, I can break it up into smaller pieces so that I can apply a piecemeal approach to it. And one of you interestingly pointed out, okay, hey, if I were to solve this problem as a piecewise continuous function, how would I do that? I will talk about it at the end. It is going to give you the same answer, but it's a kind of a roundabout way. This is a more elegant way. And as I mentioned, there are many ways of solving these kinds of problems. This is just one particular method. Okay. So this big problem here, which contains now f of t is the sum of f1 plus f2 plus f3, was broken into 4 pieces. What are the 4 pieces? In the first piece, I am looking at the response of this system only to the initial conditions. Okay, so that is the free response part of the system. The second, third, and the fourth pieces is where I switch off the initial conditions. You see, I don't have any initial conditions anymore in all of these second, third, and fourth pieces, but I tack on the forcing function, or the pieces of the forcing function. I had 3 pieces of the forcing function because 3 curves made up that total curve, and so I have 3 pieces for the forced response. And this is one of the beauties of linear system modeling. You can take a complicated system, break it up into multiple parts. Okay, this is a very powerful idea, and we are seeing the beauty of this in this type of a course, especially in system dynamics or in dynamics. All right, and then we were able to solve certain parts of this problem. We did not complete it last class. This is free response. I was able to solve it directly by using what we have done in the past. This is the forced response, the first part of the forced response. So this is solution to B. I want to point out one thing. By definition, R of t is 0 and t for t greater than or equal to 0. So by definition, this function does not have any value before time starts. Okay? So which means that I really do not need to write r of t as r of t multiplied by u of t. I do not need to write r of t minus 10 multiplied by u of t minus 10. It is kind of a redundant notation. Okay? But this is not necessarily true of all functions. So here what I would like to say is maybe, so r of t, so for example, r of t minus 10, u of t minus 10 is identical, 3 lines meaning identical to r of t minus 10 because it is kind of redundant. But on the other hand, you can also have an example similar to what I had written last class, at the beginning of last class. So if I have a function, let's say e of minus 3 times t minus 10, you will notice that this function has a value for negative time as well. It's not as if this function starts only at t is equal to 0. So for a function like this, if I have to specifically say, if we want this to be switched on, only at t greater than or equal to 10, which is the shift that I see, then you should write this as by multiplying it with this shifted step input or step function, you are completely discounting whatever is going on with this function when time t is less than 10 seconds or 10 minutes or whatever unit of time that you are using here. So as a rule, if I come across fundamental functions like the ramp function and so on, I will just assume it to be r of t times u of t. I'm not going to write the u of t from now on. But if I come across functions that are arbitrary, I mean something like this is not a fundamental function, I will write it as multiplied by u of t or t minus t naught, whatever is the shift that takes place. Okay, am I being very clear on this particular aspect? Don't be surprised if you see just r of t or r of t minus 20. You're already accounting for the fact that the ramp function is not having any 0 before t is equal to 0. Okay? So from now on, the fundamental functions that we have seen typically are r of t and then delta of t. Okay? For these we will not need to multiply by this u of t, etc. If you have a shift, you multiply it by that, but no need for these kinds of functions. All right. Then we set about solving the third part of this problem, and I will revisit that part. I will not spend too much time on the fourth part of this problem, which is solving D. We will just write out the solutions. You will see it in my solutions. So for part C, we said 3x dot plus x is minus 2. Significantly reduces my energy in writing these things. If I see a ramp function, I don't need to put the step shift on this. Okay? So I take the Laplace transform on both sides, and of course the initial conditions are 0. Take the Laplace transform on both sides. You see that the time constant is 3. And so in this case I have 3s plus 1 x of s. The Laplace transform of the shifted ramp function is nothing but the Laplace of the ramp function multiplied by the exponent to the power of the shift is equal to minus 2 constant 10s by s square. Okay, this is what we had written it out as. Then I write x of s, so this gives me x of s. Take out the factor of 3 outside so that you end up getting, and all of this is available in your post notes from last class. This is 2 by 3 s square 1 by 3. And I said, don't pay any attention to this e to the power minus 10s. Just keep it as it is. Let it be a silent observer for your problems. Once it is time to put them back, we put it back, right? So you say this is the same as e to the power minus 10s, repeated roots. Okay? Perform the partial fraction expansion as you typically would. No difference. Just forget the presence of e to the power minus 10. Calculate C1, C2 and C3. C1 becomes minus 6, C2 becomes 2, C3 becomes 6. And when it comes time to take the inverse Laplace, this is where you've got to be careful. Okay? So when I take the inverse Laplace x of t, the C1 is a constant, so you can take it out. Okay, so that's going to be C1, which is minus 2 by 3, apologies. So that's plus 6, minus 2 and minus 6 accordingly. Okay, so this becomes minus plus 6 inverse Laplace of minus 10s by s minus 2 inverse Laplace of 2 by s square minus 6 inverse Laplace of e to the power minus 10s, apologies, 10s by s plus 1. Okay, so this becomes inverse Laplace of all of these things. I'll wait for a minute or two before I move the panel up. Is it autumn break or is there an exam going on as well? Oh, they have an exam before autumn break?
Yeah.
So a farewell gift? Okay. So I guess maybe I want to spend, since I have you all, and I see that you're here in spite of an autumn break looming on you and an exam even more so looming on you. What ails people these days? What is the problem with the system? Do you see a problem with the system? Is it too much work? Is there too much homework, too many things happening at the same time, or is it just prioritization of your limited resources? Is that what's going on? Both? Option 2?
More teachers. Not you. You're the
Oh,
best.
well, yeah. This is getting recorded, so you can say all the nice things you want. I can see it's maybe a combination of several factors, but I think it's also a learning experience, knowing to prioritize your limited resources. All right, I'll move on. Happy to have this discussion after class, after hours. I believe I might want to raise the board a little bit just to write the inverse Laplace. I think, did everybody get those last few lines? I believe we did this previously as well, so just bear with me, I'll complete this and we'll move on to better things. Alright, so x of t for the third part becomes 6. Because I had an e to the power minus 10, I have a shift taking place, and the first one becomes a step function because the denominator was 1 by s. Okay. Second one is a ramp function, minus 2 r of t minus 10. Last time we multiplied it by the step shifted function, but we don't need to because we know the ramp function starts from t is equal to 0. Okay. The third one becomes the following. 6 e to the power minus 1 by 3 t minus 10. Watch this. I have to multiply by the shifted state. Okay, because this is an arbitrary function. This is not a fundamental function. Okay, so this is now multiplied by t. Okay. Yes, please.
So, y'all know that 6 is also greater than 0. So, like, can you just write 6 instead of writing 6 times t minus 10?
One could do that, but then one has to be careful, because if I just write it as 6, then does that magnitude of 6 start at t is equal to 0, or does it start after t is equal to 10? You see, so this portion of the response is not active when time is less than 10 seconds. It switches on only after that. It's almost like you have an electrical circuit. We're going to circuits next week or the week after. When you have a circuit with a resistor and a capacitor, typically you start off without the capacitor having any charge. It is completely discharged. Then you switch on the battery, the capacitor getting charged up, right? So there is a certain delay in the proceedings taking place. So this shift is to accommodate for such delays. Okay. All right, I have the last one. We'll do that quickly. So I'm just going to look at this piece here. Take the Laplace transforms on both sides. Okay. So this is for piece number D on the other panel. Laplace transform on both sides. And bring everything onto the other side. I have minus 20 Laplace transform of the shifted step function. So that's going to be minus 20 e to the power minus 12.5 s. 12.5 is a shift, divided by s. Because it's a step function, there is a denominator term s, and then s plus 1 by 3, and this numerator is minus 20 divided by 3. Okay? Time constant is 3. Okay, so this is for piece number D of the problem. We do the partial fractions as if nothing has happened, pretend as if this e to the power minus something doesn't exist, and so you write this as minus e to the power whatever that is, 12.5 s, and then this is 20 by 3 s times s plus 1 by 3. This is identical to the same thing. And probably some C4 by S, C5 by S plus 1. Are there any fundamental questions on the partial fraction decomposition? Is everybody clear with that? There are distinct, real distinct roots, real repeated roots, complex conjugate roots. Now you know MATLAB as well. You've taken the quiz hopefully, or you will be sometime soon, tonight, before tonight. Just calculate C4 and C5. Calculate C4 and C5 as usual. I wanted to do MATLAB today, but I knew that there might be lesser number of people coming, so I'll wait until more people come, okay? So that it's more useful and I don't need to repeat myself 25 times. All right. So I take the inverse Laplace and I write my total system response as the following. Okay, this is including all the 4 pieces. Okay, this is total system response. I want to point out a few things here. Okay, x of t after everything has been done. Free response, which starts at t is equal to 0. Okay. Then I have this ramp part of the response, 2 times r of t is input there. So I have this is going to be 6, I guess 2 times r of t minus 3 and plus 6 e to the power minus t by 3 u of t. This is the response to the forcing function f1. Then the second one is 6 u of t minus 10 minus 2 r of t minus 10 minus 6 minus t minus 10 by 3 u of t minus 10. That was the response to the third piece. And then the response to this particular piece here, the first one gives me a shifted step, the second one gives me an exponential with it step, and then plus, eventually this is what you end up getting. It's going to be 20 e to the power minus t minus 12.5 by 3 minus 20. Okay, this is a response to the last part. So this is actually C5 and C5, 4 and C5. From what we've done here. Complicated problem. It looks simple. It's a simple first order lousy thing, right? It's a first order ordinary differential equation with a forcing function, but you look at the response, this makes absolutely no sense. Right? But it's a response to a complicated input. The system could be simple. That does not mean that its behavior is going to be simple. Okay? Its behavior is a function of the input that is given to the system. A couple of things I want to point out. Maybe the more important thing here is r of t minus 10. How do you write this thing? One way to write it is just by r of t minus 10. Okay, it's accepted, that's the way to write it. But by definition, r of t minus 10, watch this, it's 0 before t is equal to 10 seconds. Or 10, whatever, minutes, I guess, whatever it is. It's t minus 10 when t is greater than or equal to 10. That's important to recognize. It is not just little t when t is greater than or equal to 10. It's t minus that shift that you're applying, because if I plot this function, r of t minus 10 does not have any value before t is equal to 0. Right at t is equal to 10 seconds, or before t is equal to 10. Right at t is equal to 10 seconds, it starts, goes off as a ramp function. Okay, so that's something to keep in mind. And I want to erase this portion of the board so that I continue writing certain parts of the response, the transient and the steady state part of the responses. So what are the transient parts? E to the power minus t by 3. Okay, as time goes to infinity, this part vanishes. So that's a part of the transient response. Then, do I see anything here being a part of the transient response? This is 2 times 3, that is 6. But that's always going to be switched on from t is equal to 0. So that's why I don't have a shift function on this. R of t ramp function is always switched on. As I go to infinity, it does not decay or anything. And so that is not a part of my free response, but this is a part of my free response. So this is plus 6. All of them put together u of t, because the initial response also starts from u of t. So in reality, this should be u of t here. Anything else that could be added on to the transient response? I see all exponential terms that could be added on to the transient response. Okay, so look at this. This term here, t minus 12.5 divided by 3, as time goes to infinity, this term also is going to drop down. Okay, so that's also a part of transient response. So I'm going to have plus 20 t minus 12.5 by 3 u of t minus 12.5, start big brackets here, and any other terms containing the exponential term. So all exponential terms which have a negative exponent, they decay to 0, even if they started off after 10 seconds or after 12 seconds. Does not matter when they start. You look at what happens when time goes to infinity. If these things decay down. So I have minus 6 minus 3 minus 10 by 3 u of t minus 10. So those are all parts of the transient response. Any questions so far? Anything that is an exponential decay is a part of the transient response. What's a transient response? All parts of the system solution that decay to 0 as time goes to infinity. Okay, that's all a part of your transient response. Whatever is left over is a part of your steady state response. That steady state behavior could be blowing up to infinity. We do not know. Okay, so a term like a ramp function here is obviously going to go to infinity as time goes to infinity. A steady state part of the response is the part of the response that is still there when time goes to infinity. Okay, so if I look at that, I have the following. Another big set of terms. So 2 times r of t minus 3. You can put a u of t there because there is a 3 there. So just to make sure that this starts from time t is equal to 0, you can do that. Then I have 6u t minus 10. This is a step function, but after 10 seconds, this switches on, and as time goes to infinity, this still remains. Okay. Then I have 2 more pieces there, minus r minus 2r of t minus 10, that's one piece, and then the last one, 20 u of t minus 12.5. This is all steady state. This is all fancy. Okay, and in this problem, this is the free response. And all of these forced response. And it is typically only for linear systems that you can have the response split into these pieces. Okay? For nonlinear systems, the distinction is a little more harder to imagine. It's not like it's not possible for certain nonlinear systems that has a closed form solution, and there are some of those. This distinction is possible. All right, any questions on the problem we have solved so far? Any questions, please? While I erase this board, if you want to think of some questions. And something I want to point out that we kind of take it for granted in system dynamics is there are systems whose behavior right at the start of the initial conditions is not necessarily the same as when the input starts. That is, there are systems that are called non-smooth or discontinuous systems. Okay, the system response is discontinuous, and the idea is that the initial condition at time t is equal to 0 this is from the free part of the response. Okay, it is at loggerheads, it's not necessarily equal to, but it's not the negative, or it is not whatever happens after the forcing function has started. So x forced at t is equal to 0. Okay, you take all the forcing parts of that function and you substitute t is equal to 0. It should either give you something that matches with the free part of the response so that you get back your initial conditions, or this entire thing should go to 0. Okay, it should not even act on the system. But sometimes for certain systems this is not the case. And common examples are, you take your chalk piece and you write on the board. I was not able to make that squealing noise, but that is called as stick-slip friction. That is, as I am writing, I am in a state of static equilibrium when it is sticking, and as I am moving right from that stick to that slipping part, I am in a state of dynamic motion. So there is a discontinuity in the system response. And that's what you hear as a chalk squeal or a brake squeal is an example of a non-smooth system. Not a part of what we are studying, but keep that in mind as well. Okay? All right. In the interests of time, so here are the choices I present to you today. It's up to you what you want to do. I could either take another forcing function f of t and break it up into a couple of pieces to show you how this is done, this process is done, or I could start second order systems. Anybody want me to do one more example of this type of a problem? So you're all outnumbered. The people who want an example are outnumbered. So I'm going to do second order systems, but to also help you out, I'll post a couple of examples that I've done already. Okay? So I'm going to start second order systems. It's a slightly new thing for us. Before I start second order systems, fundamental characteristics of first order systems, just to keep a recap. To designate a first order system, how many parameters do I need? How many parameters do I need to specify a first order system? Anybody? 1. I just need a time constant. Okay? So only one parameter. Which is called as the time constant tau to identify first order. Okay, this is one difference between the first and the second order. In the second order system, I need 2 parameters. Easy enough, right? The third order system, I need 3 parameters, hopefully. We don't know. So second order systems, you have 2 parameters to identify. This is called as a system identification process. You identify what is the nature of the system. Any ideas on what those 2 parameters could be for a second order system? This is something you would have come across during the last part of your dynamics, 2030. Towards the end of your dynamics, yes.
Time and position.
Time and position is always there for even a first order system. Right? I mean, I need to know what the position of the system is at this particular instant. That's always a problem. That's something I need for the second order system. And so what I'm saying is, okay, somebody is telling you, hey, I'm going to give you 2 parameters, a number 25 and a number 0.6. Build a second order system model. If that person had told me, hey, I'm going to give you 1 parameter 3, build a first order system model, I would say 3x dot plus x is equal to f of t. Simple. Because if it is a first order system, what is the parameter that's given to me? It's the time constant. If it's a second order system, the 2 parameters of importance, anybody wants to take a guess? Yes?
Basically the damping and the response, or a fancy thing that basically is it going to follow the normal exponential downward? Is it going to go spinning back and forth? Is it going to be vertically damped, under damped, or over damped, or whatever those 2 names are?
Okay, that's an interesting observation. So damping has something to do with it, absolutely, yes.
I was thinking position and velocity.
Position and velocity. So I guess to identify a system, right? What we are not trying to say this is how the system behaves. So we are trying to identify. Okay, I'm giving you 1 parameter. Build a first order system for me. Okay, I'm given the time parameter. I can build a first order system. What I'm saying is, okay, if I'm given 2 parameters, build a second order system. What are those parameters that could be? damping and system response, you're getting there. Anybody else wants to take a last guess? Yes, yes.
Would there also be a time constant for the second ordering?
It wouldn't be a time constant. It would have something to do with time, obviously. Yes, one of those parameters. Okay. Yes, yes.
Frequency.
Frequency, very nice, very nice. What type of frequency? Natural frequency. Every second order system has a natural frequency, omega n. And damping, it's damping ratio, it's not the damping constant. Okay? So there are two parameters which are called as zeta. This is the Greek letter zeta. Alright? And when I write it fast, it becomes a little crumpled. So please watch out. And then omega n. Omega subscript n. Okay, n stands for natural, omega stands for frequency, so natural frequency. Okay, simple enough. Alright, so how do we construct a second order system? And you've seen this in dynamics, at least partially in some sense. Let's do it this way. And here is something to keep in mind as well. Okay? You take any system, a system can be modeled as a first order system. You take any system, that system can be modeled as a second order system. You take any system, you take the human body, it can be modeled as an nth order system. It can be modeled as an infinite order system. The closer you get to infinity, the closer you are to approaching the real behavior of the system. Okay? Certain systems, first order modeling is sufficient. Certain other systems, I may need to do second order modeling. And for the most part, these two system models are sufficient to describe even very complicated phenomena, very complicated systems. Okay, that is the beauty of system modeling, which is what we are coming to. Spring mass damper. Mass, stiffness, C, force. By now you should know this equation by memory. Can somebody recite this to me? What's the equation of motion for this system? Yes?
Ft equals mx double dot plus cx dot plus kx.
Fantastic. This is the equation of motion. Okay? And if this is not very obvious, please make sure it becomes very obvious. If you've solved more complex problems than these, but please make sure you know how to do this inside out, backwards, front, in your sleep and in your dreams. How many initial conditions do I need? This is a second order system, so I need two initial conditions. Right? So this is x of 0 is equal to x naught. X dot of 0 is some v naught. Okay? What we want to do is, we had written a first order system in its standard form. And standard form of a first order was tau x dot plus x is equal to something. I want to do something similar for this system as well. And you've seen this process in dynamics, but we will still go over it. I'll bring this down. Right. So standard form of second order systems. Now there are different classes of dynamicists. Some of them like to write it in one way, some of them like to write it in other ways. I'm part of a culture that likes to write this in a different way. Okay. So we will stick with what your book says, which is the basic standard form that everybody else likes. I start with the first equation of motion that I have. Okay, then I divide through by the mass. One by m times f. Okay. Then I take a look at this term K by M and see what its units are. Unit for stiffness is newtons per meter divided by kilogram. Okay. Newtons, I can write it as kilogram times mass meters per second square, because it's mass times acceleration, right? So this is kg meters per second square multiplied by meters per kilogram. The kilogram cancel. I'm sorry, this comes to the denominator. Kilogram cancels off, mass cancels off, so this term becomes a 1 by s square term. Which means if I take the square root of k by m, it has units of 1 by second, which is units of frequency. Okay, cycles per second multiplied by 2 pi, or 1 by second, you call it as hertz. Right? You've come across this before. So we say k by m is defined to be a term omega n square. Okay? So what are we doing? We start off by saying, okay, here is a second order system. How many parameters do I need to design it? I need 3. Mass, stiffness, damping constant. 3 is more than 2. So I want only 2. And mass, stiffness and this, damping constant, I mean, these are like completely arbitrary numbers. Do they have any inherent property that has to do with the physicality of the body? Probably not. So natural frequency is something that's a fundamental property of the body, right? So in that sense, this is nice for us. There's one here. Substitute this back. So that's x double dot plus c by m. Look at this. I'm going to multiply by 2 and divide by 2. Multiply by omega n and divide by omega n. Just for fun. Multiplied by x dot, of course, plus omega n square x is 1 by m f free. Okay. Look at this quantity, c by 2m omega n. Okay. Units for c, Newton seconds per meter. Okay, this is the damping constant, right? It is force times the inverse of the velocity. Then I have omega n is 1 by second, mass is kilogram. But newtons I can write as kilograms times meters per second square. So this is Newton, I'm sorry, meters per second square times kilogram, multiplied by, I have a second there, this has to be 1 by s. That is 1 by s is the unit for omega n is in 1 by s as we have seen there. Then this is s, seconds here, kilogram, 1 by second. 2 is a convenient number, so we'll just leave it as it is. It does not have any dimensionality. Once again, what did I do? Damping constant, Newton seconds per meter. Okay, mass, kilograms, frequency, omega n square is 1 by second square, so omega n is 1 by second. Then newtons I write it as kg meters per second square. Okay, I look at all these things, and I have a meters which I forgot to write because it's there in the denominator. Okay, that cancels off with that. This is a second square. 1 by second becomes a second, couples with the second on the top becomes a second square. So this is dimensions, which is quite nice, because now I have 2 parameters instead of 3 parameters. One of them is dimensionless, which means that it is agnostic to the type of a physical body or a system that you are studying. You can use it for a human body, you can use it for a pendulum, you can use it for a door, you can use it for a heat engine, for all that you can. The other thing is a natural frequency, which is an inherent characteristic trait of a system. And so, here I have two parameters which make more meaning, which make more sense, so that I can take any kind of a physical system and model it as a second order system. I don't need to restrict my attention to just springs, masses and dampers. Okay, so now if I rewrite the system, this creature is called zeta. When I was growing up, Catherine Zeta-Jones was one of my favorite actors. So it always brings back good memories. Maybe you don't know her. Maybe I'm too old. Alright, so this is called zeta. Okay, this is a dimensionless parameter. So that my system equation now becomes the following. It's x double dot plus 2. You'll see the reason for that 2 very soon. Okay, looks quite arbitrary, but believe me, it is not. There is an omega n that is snuck in there, right? This is omega n by omega n. This creature is what we handle here. This is called zeta. Okay, x dot plus omega n square times x is 1 by m f of 4. This is one way of writing the second order system. So this now represents any generic second order system which is characterized by two parameters, omega n and zeta. Omega n is a natural characteristic of that system. It can be the characteristic for any system. Zeta is a dimensionless constant, can be used to characterize any kind of a system agnostic to applications, and this is a very powerful equation. This same equation can be written in many other books. It is also written in the following form. We are not going to use it, and this is not the form I grew up studying and using in applications, but this is convenient in your book. So we also have this following form. 1 by omega n square x double dot zeta by omega n x dot plus x is equal to 1 by k f of t. They are both the same things. In one, I just have omega n square multiplied throughout, but if I take omega n square and divide it throughout, I just get the second form that I've written. So don't be surprised if you see this form. Don't be surprised if you see this form. They are both the same things. Okay? Just for a note of caution. All right. So what is our business here? So I want to write a couple of things before we quit. So if I have a first order system, I need one parameter to characterize it. One parameter, tau, to identify the system. Tau is a time constant. Okay, time is a universal character, right? So it makes sense to have something that is universal. Time does not care whether you are modeling a human body or whether you are modeling a squirrel or a tree. Time is time. Okay, second order system. You have zeta, you have omega n. These are the parameters, so two parameters. To identify system, and the fundamental difference between a first and a second order system, the biggest difference between a first and a second order system, and this is something that is just naturally seen, is that second order systems are capable of oscillatory behavior. First order systems cannot produce any oscillations whatsoever. They will either ramp up, go to infinity, or they will die down. If I have a sinusoidal input, that's a different story. I'm talking about a natural response. Okay, naturally, if I don't have any input functions on my first order system, all it can do is just die down. Okay? Or if it is an exponentially unstable system, jump up, go to infinity. It will not oscillate. Okay, so fundamental difference. If at all anything you take from this course, is this line. The natural response of second order systems can, under certain situations, exhibit oscillatory behavior. The free response, free or natural, that's another name for a free response. Natural response of second order systems, of second order can exhibit oscillations.